This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. All right, let's get started. It's great to see such a turnout. It's such a great hour that we have. And I will warn you that the computer here, PowerPoint, was just crashing randomly when I was flicking through slides. So if you see the slides go down or whatever, you have to let me know if I don't notice it. Okay, or I may see the blue screen of death up here. So this is a fairly high-level lecture to motivate why we're studying cyber-physical systems. It's here to pump you up a bit, really, and to say that you're doing the right thing by getting into this area, by studying the Masters of Engineering, Electrical or Mechatronics or whatever. And our reference is Chapter 1. But I'm going to talk about many real-world examples. There's some very basic info on the slides, but what I want to explain is a lot of the underlying stuff that's going on around the world. So I showed this. Uh-oh. There's stuff happening here. Yes, some device just popped up randomly. Okay, so I showed this slide last time that cyber-physical systems have these inherent contradictions to them. And you may think that some of these things are not necessarily cyber-physical systems. So one of the ones we might think of is energy, perhaps. Maybe let's not think of, say, a spinning wind farm, which is clearly a physical system and has dynamics to it, but perhaps something like a solar farm. And the way the power system has changed in the last, whatever years, decades, is it's gone to very much a more distributed model, okay, particularly with renewables, which are going to be the next big thing that you guys will probably be working with. Okay, so instead of having these massive coal-fired power stations in Australia anyway, and only a few of them littered around, we now have very decentralised wind farm, solar farm, and even worse, solar panels on people's houses with their own inverters and all of that sort of stuff on there. So that's a classic example of a cyber-physical system, right, where new things are being added to the network, the power network, on a day-by-day basis, and things are dropping out, right? As people disconnect their solars or reconnect their solars, a new wind farm comes online. It's a dynamically changing system. Now, underneath all of that, the infrastructure of this power grid, if you think this nebulous grid thing here, is software. And the software is written by who? Computer scientists, software engineers, people that hack code and don't look outside of a computer screen, right? And a lot of the things that they may be coding for work nice in simulation, but when you have a real-world system where the dynamics are changing all the time, new things are being connected, removed, and the loads are changing, that software may not work very nicely. In particular, we'll talk about that. I'll give you some examples in C where things can go really wrong, where you don't think that they would. And it could be catastrophic. Okay, you can see all these examples up here. There could be some death and destruction involved, or just simply blowing things up. If you grab a generator of electricity, a wind turbine or something, and you just shove it into the network, we all know that motors, when you spin them around with a bit of force, they generate EMF, right? Electromotive force, but the opposite can happen as well, right? If you put power into them, they can spin up as well. And if you don't have a system that's adaptable enough to deal with the changes and switch between different modes of operation, you could very well have generators being put into the network which end up turning into loads. And that's not a good thing, right? You're hooking up a new wind turbine into the power network, and because of the setup of the system and the dynamics and all of that, it becomes a load. It starts sinking power to it. Okay, so some of these things are not as obvious as others, but they are all cyber-physical systems. And our task as engineers is to really orchestrate the networked part of it, so the connection between the cyber part, the computer part, and the physical part of whatever's going on here. Now, I'll talk a little bit about what I call hacking later on. Hacking, not in the computer science, got to break into some account perspective, but hacking in terms of just putting things together and seeing if it works. That doesn't work anymore. It only works maybe in some pracs or something you do at uni where you're putting some LEDs together, and if you put the LED round the wrong way and it doesn't light up, you just turn it around. No one dies, right? These systems here are super important. We can't just hack them together and see if they work. So we need reliable tools, reliable methods to ensure that we model them properly, we design them properly, and any analysis is done in order to know the parameters of their operation. Okay, so the hype around the Internet of Things. Using internet technology to connect physical devices, things. It's such a dumbed-down concept, and that's why it's hyped, right? Hype stuff generally tends to be very dumbed down. And there's a nice little graph here on hype cycles. It may be a little difficult to read, particularly from the back, but the x-axis along here is the innovation. It starts off at innovation trigger, where an idea is born. And then we move across to my favourite, second favourite area, the peak of inflated expectations, where if you're measuring expectation on the y-axis, people just go bananas over it. Oh, it's going to be the next ... Okay? So there's various things on here, quantum computing, etc. But right up the top here, according to these people here, is the Internet of Things in the next, and it's going to be sliding down. This diagram is a few years old now, and there are forecasts on these particular things of the range of 5 to 10 years. So Internet of Things is really at that peak and probably sliding down. And where's it sliding down? Into the trough of disillusionment down here, where people go, oh, it didn't really solve all the problems. Let's get on to the next innovation trigger and hype it up and get into the peak of inflated expectations. Okay? So this subject is not about Internet of Things. Okay? That's just a name put on a bubble that's happening as an example of cyber-physical systems. Okay? There's the good old trough of disillusionment. And you can see where some of these things have fallen. You know, cloud computing, NFC, I mean, really that was going to be the big thing. You know, near-field communication. Maybe it's on the rise again now where you can do contactless payments with your phone and such like that. Okay? And speech recognition and things like that are finally coming back again. That speech recognition was the big thing back in the 90s. I remember having an old computer with speech recognition software on there, dictation software, and it was the next best thing. And nothing happened with it for sort of 20 years, and now it's starting to take off again. All right, so just to really push this point home, IoT is the use of internet technology. Internet, it's a specific lockdown type of technology, okay, for cyber-physical systems. So if you've bought a textbook ever, you might wonder how on earth are these things printed? Gone are the days when it used to be you'd build up a typeface and the thing would go and sort of stamp pages or something like that, and you'd have someone feeding the paper in the machine. All gone. Here's a printing press that is made by Bosch. It's a cyber-physical factory. There are hundreds of microcontrollers in here controlling the operation in order to print out your books, basically. Now, the technology that's used now is inkjet printing, interestingly, a variant of that. Not your consumer, sit at home, watch the printer spit out pages, but a sort of a more evolved version of inkjet printing. And in order to get this stuff done really quickly and mass-produce books, right, it needs to be done with high precision. So you've got hundreds of microcontrollers in here sensing various things. You have reams of paper which are several tons. Okay? You don't have people carrying them and putting them in anymore, feeding single sheets in. These are several tons. Think of the dynamics of a big thing of paper weighing several tons, trying to spin that around or even just get it lined up into the machines. The paper spins through this machine, and I'll show you a little picture of it in a second. It spins through here at about 100 kilometres an hour. The paper is going through. So what happens when the paper runs out? You can't have the world's biggest roll of paper. It's spitting out at 100 k's an hour. What happens when it gets down to the core, or whatever you want to call it, where the paper sits on? What happens? Do you turn your machine off, unclip it all, go load another thing on? No, that's not very productive. You want to keep these things going 24/7, printing your books, getting as much money out of the machinery as possible. So what do? Well, you have an intelligent system that can essentially detect when it's getting close to the end of a ream and have a backup ream sitting there of paper, spin it up to the right same speed as the feed that's going out, and then magically seamlessly join them together. And you think about that. It's going at 100 k's an hour, this paper. And you have to somehow line up and drop in and attach via some tape. It's actually taped together. Tape in there the next ream. So it's like, it looks like one continuous stream. That's crazy. If you want some numbers on it, you need about 2 millimetres of precision. If you think about a car driving at 100 k's an hour and you had to measure it or something, or stop it or something to 2 millimetres precision, that's amazing. You've got about something like 10 microseconds or something to get the accuracy there. So these machines here, they're networked, okay? They all need to talk to each other. Those yellow cables are ordinary Ethernet cables, and it's using TCP/IP. So maybe you can call it Internet of Things sort of setup. But for those of you who've ever dealt with TCP/IP, it's terrible, okay? Internet relies on TCP/IP. Dropped packets, reloading pages, weird stuff happening. Packets just disappear and never come back, right? So how does this really, crucial machinery here actually function at this high tolerance? Well, it has some additional layering on there. So it uses high precision, where's my mouse? I can't even see it. High precision clock synchronization, which is an IEEE standard, and it uses a isolated LAN, right? You want to have as much control over that setup as possible and get things down to sort of, nanosecond timing between events and things like that. But there's more. Let's have a look at the actual internal here. So I will harp on again about IoT represents the technical solution. It says internet technology in the problem statement to connect things. It's kind of weird. It's giving you the solution in the problem. So that's why we're going to call this a generic cyber-physical system. So this is what it looks like. You have your active paper feed spinning around. Okay, it's unloading upwards if you like. It's very hard to do this with the mouse. And you've got that reserve paper feed sitting there, ready to go. It's ready to drop in at a moment's notice. It has the tape sitting on there, sticky tape, to join and seamlessly stick onto the previous part. So you are creating a continuous roll that goes through here. There's lots of things to think about though. What happens if something goes wrong with this machinery? Is there just some big red stop button that you can just hit stop and everything stops? Maybe, but that's probably only in a very bad emergency. Designing such a system like this, even with all those tight controls on the timing and automation and everything, still means that you have to think about emergencies. You cannot just stop and, if this thing goes nuts or something, or if the tape doesn't stick and suddenly some loose paper comes into the system, you can't just stop things. These rollers, the machinery in here is hot. If you just stop and just leave paper sitting in a hot machine, it catches fire, okay? So you have to think about creative ways of shutting this machine down in a safe fashion. And that's about talking about safety and reliability. That's going to be one of the topics later on in the subject here. That's something else to think about. So here's our flying paster, if you like. It's got the cutter. So once this is getting close to being exhausted, this will cut it, and it makes sure it doesn't cut it in the middle of a page. Okay, you don't want your book to be half a page joined with a piece of sticky tape on there, right? It's not going to be a very nice book if it does that. So it's got optical sensors in there as well that can detect when there's a blank bit of the text to slice it and cut it in here. And we have, obviously, a lot of physical stuff going on. Dynamics of these rollers, motors, we have to model and then analyse how it's all going to work. And then there's some adjustable things in here to adjust the tension of the paper. It's another thing as well. If you're just cutting this fast-moving piece of paper and you are sticking another piece on there, you are essentially putting a disturbance into the system. Okay, so you have to compensate for that somehow. And this dancer unit here can adjust the tension of the paper as well. It's an amazing little system. So let's have a look at the thing in action. It's noisy. So that's the main. That's the paster bit coming in. That paper's spinning through very quickly. That's the reserve roll, spinning up to speed. And then, done. and the machine just keeps printing. That's travelling at 100 k's an hour, that paper spinning around there, and it was seamless, right? It just kept doing its thing. Amazing. So that's a little cyber physical system there with some very, very difficult technological issues to overcome. Okay, so you guys, sorry, I didn't want to show the video just yet. You guys are going to be looking back, maybe in 20 years' time, looking back at a video like this and saying, why did this sort of thing ever happen? 99 or something % of accidents with cars and trucks and all of that are caused by human error. Yep. This is preventable. This sort of stuff is preventable, right? Cyber physical system, well, the challenge of that is to stop this stuff from ever happening. Okay, they say in Australia now we're trying to reduce the road toll. Well, most of the problem is driver error. If we can get autonomous systems or safety systems more involved in the car, and I'll talk a bit more about them in a minute, you know, by the time you're my age, you'll be looking back at this video and thinking, geez, this looks like the 1800s here. You actually had car crashes back then? I mean, really? They're just not around anymore. Okay, so the problem is, though, in any large-scale company or project or whatever, you end up with all these people doing their own little tasks. Typically, you don't have someone that knows everything about a project. And obviously, the bigger the project gets, the harder it is to have some chief architect that can see over the whole project. And you get these people making the assessments. Oh, yes, the tusks, that's a spear. And the trunk, well, this looks like a snake at the macro level here, or even at the micro level. And if you want to put it in the engineering context, this is what happens. We get people saying, oh, it's a small computer, there's a network here, there's a robot on this side, and not seeing the bigger picture and how these things integrate. This is most common with programmers. I'm not going to be mean to programmers, but they live in this rarefied atmosphere that everything is perfect. Machines, you code it, you simulate it, or whatever, you run a bit of code and it spits out the right answer. It's always going to work. In embedded systems, that's just not the case. Okay, maybe on a really souped up piece of hardware like a PC or something like that, it's going to work all the time. But in an embedded system, weird stuff can happen. Okay? I'm going to talk a bit about the societal challenges, but one of the drivers, I guess, or drivers, funnily enough, one of the sort of the big things that's happening now is the whole automation of driving, and that goes with that freeway crash that you saw there. That automotive CPS addresses a lot of the societal challenges. So things like safer transportation. We could, in theory, get rid of driver-caused accidents. We could even assist with energy efficiency. Humans are notoriously inefficient drivers. They really are. Accelerator, brake, not reading the traffic, right? And you flat to the accelerator, flat to the brake, right? That's not very energy efficient. If there's some sort of algorithm that could actuate the accelerator and the brake to be more efficient, sure, that's a cyber physical system. Even climate change, right? Well, if you don't like the term climate change, reduction of pollution, maybe. That's also a cyber physical challenge. Really? Is it? Sure is. Cars spit out ugly stuff out of the exhaust. Nitrous oxide, carbon monoxide, whatever HC is, hydrogen something. I don't know, I'm not a chemist. But if you plot basically, so along the bottom here is the air-fuel ratio. So it's the percentage of air to fuel that's getting injected into the cylinders of your car. And you look at how much is being removed from the noxious gases. So this is cleaning rate. This is not percentage coming out. This is kind of the opposite. It's how much is being removed. There's this optimal window called the stoichiometric ratio, Stoke, as the automotive guys call it, because they can't be bothered saying stoichiometric. I think it's about 14.6 or something, but it's in a range. So if you can control your car, the air-fuel ratio, to be in this range, you are obviously emitting much less pollution. Why is it a cyber-physical system? Well, you've got moving parts. You've got an intake manifold that can adjust the amount of air coming in and can measure, via sensors, the airflow, right? The mass density of the air that's coming through. You've got your combustion chambers, the cylinders, and the pulsed fuel injectors that are pulsing fuel into the cylinders. And on the exhaust side, you've got a measured airflow and also oxygen sensors to pick up some of those noxious gases there and work out what they are. And underpinning all of that, you've got software. You've got people that have come and written the code that determines how to adjust both the air and the fuel, the ratios of those, into the cylinders in order to get the perfect Stoke ratio back here, right? To get it in that window. Now, that software is something that, if it's written in C and running on a microcontroller, more about this next week, there's a set of instructions that run at a particular time. Okay, just a set of instructions, a C code, just running instruction after instruction. How does it interface with something that's continuous? Okay, you're continuously measuring airflow on both sides of the vehicle here. Sure, okay, analog digital conversion, yeah, that's fine. But there's some very subtle nuances there about timing. When are you going to be sampling the airflow that's coming in and out of here? How does that relate to some master clock that is directing the operations of the software? Okay, this is a hybrid system. All right, and we're going to talk a bit more about this later on. Now, this will really pump you up. So, McKinsey. If you get to work for McKinsey, you'll be lucky. Massive company. People, if you climb the ladder in McKinsey, you'll do well. So, they came up with 12 potentially economically disruptive technologies. 12 of them here. Basically, if you get into one of these, you're going to be a gazillionaire. You are. Because they're going to be economically disruptive, right? Right, there's no lawyer, nothing like that, no medical people really on here, right? This is all technology stuff. By my count, 8 of those 12 have major cyber-physical system components to them. Major components. Okay, mobile internet, the Internet of Things, my favourite. Advanced robotics, that's a given. Autonomous vehicles, obviously. Energy storage, yes. I'll give an example of that. 3D printing, advanced oil and gas, and renewable energy, as I said before, is a cyber-physical system, right? You've got the interface between physical world and some scheduling algorithms and things inside the power plants, okay? So if you want to be rich, you're basically in the right area. You've got a 2/3 chance, right? Because cyber-physical systems are 2/3 of these things here. And if you want some figures on this sort of stuff, right, we're talking trillions of dollars of trillions of dollars of money over here in terms of the things here. And you look at the scale of these things. Internet of Things, 1 trillion things that could be connected to the internet. Holy moly, right? This is a major technological disruptor. It's going to change the way we do things, right? Yeah, cloud technology, maybe not so much. But advanced robotics, autonomous vehicles, and in particular, this so-called Internet of Things. All right. Now, big companies aren't dumb, are they? They've got smart engineers working for them. So, of course they're going to get into those 12 areas, right? Because these are seen as the emerging, big disruptors. Google. What can I say about Google? Good old Google. All right, so where do we start? Obviously, Google have been developing a robotic car. And unfortunately, they've found that it's pretty hard to mimic how humans operate the car, right? I guess we're a physical part of the car, right? We are the physical part of a cyber-physical system of the car, where the cyber part is perhaps stability control and things like that might be part of the car, or even the engine scheduling and all that stuff. So they found it's pretty hard to mimic human behaviour and our sensory stuff. So, even a simple little electric car that looks like a Prius there has something like, $150,000 of equipment in it in order to just have enough sensory data to not run over some witches' hats or cones or whatever on the ground. Okay, there's a LiDAR system on there that's basically, rotating and scanning, a laser radar that's for range finding and measuring the depth of things there. So it can be made more superior than us too, right? We don't have eyes in the back of our head, and if we're still looking in the mirror to see behind us, we're not looking forwards. But with 64 lasers that may be sampling in front and behind simultaneously, obviously there's scope for a car to be superior to what we can do in terms of our sensory functions here. So Google are pretty smart. They know all the money's in here, so they've gone down the sort of autonomous vehicle route. They've also gone into your homes as well. And about 5 years ago, they purchased Nest. Now, what were Nest? Nest were a company that made smoke detectors, like Internet of Things type smoke detectors, and thermostats. They're very big in the US. You go in a lot of houses in the US, and they've got a Nest thermostat on there. So Google was smart that way as well, thinking, well, if we can own the means of transportation down here, and we can own stuff in your house, and since then Google Home has come along and it's now been rebadged as Nest anyway, which is funny. You can own your home, and they bought Boston Dynamics, which is a military manufacturer of robots. Several years ago as well. So they own the military as well in some sense. So, right, Google aren't dumb. They realised that robotics, autonomous vehicles, and Internet of Things, connectivity in the home, that's where they're putting all their resources. Likewise, with our friends at Facebook, Facebook tried to buy a drone company. Now, this is a very special drone company. It's an autonomous drone company that works on solar panels. So you can just launch the thing and leave it up there for a few years, and it does mapping and stuff like that. But Google grabbed it because they like maps and stuff, and they said, we'll use it to, we'll use it to map places. Really? Yeah, sure. Monitor remote regions. In other words, spy on things. So they've got control of the mapping infrastructure as well. If you want your maps, pretty much Google's the only place to go. Apple Maps, they're still pretty crap. Anyway, Tesla got into it as well. Batteries. We need batteries for our cars. We need batteries for storing solar power in people's homes, Tesla walls, those sorts of things. So they've got this massive gigafactory in the States there, right? And where's that sit? Energy storage. They're cornering that thing there. And these big companies are not dumb. Lastly, obviously, there might be an Apple car coming along one day. they're not dumb as well. They're putting big resources in there. Recently, they just pinched a senior exec from Tesla. So it's pretty obvious that that's what they're doing. All right, so I want to show you how things are changing. Backbone, infrastructural core, server rooms, big ugly server rooms with fans in there to keep everything cool. That was the infrastructure. You would have big rooms that are dedicated to everything comes out of that room, right, for perhaps one company or something like that. Massive infrastructural core. And then we started getting mobile access. This stuff is probably what do I say? You guys are probably so used to this stuff. I do remember a time when there was no mobile phones. And I remember one of my friends did get a mobile phone back in the mid-90s. And he brought it to school one day, and I thought, why have you got a phone? And he just said, it's out there, it's new, or whatever. And I just thought, no one could call him, right? Because no one else had a phone. So he'd just be walking around with this phone all the time. And we're talking about one with an orange screen on it, right? It didn't even have colour or anything. It was really weird. And it had a pop-up aerial and all that. But anyway, so then along came all their mobile devices, and they're still connected to that core. And on top of that, we've got the outer layer called the sensory swarm. So these are all things like all your sensors that guide our actuators. Cameras, biomedical devices. Give me a little mouse here. Biomedical devices, things like that. Cameras, etc. All going all the way around here. But that is it's really weird. We've kind of gone out to this distributed model in terms of the sensors now are everywhere. They're ubiquitous pretty much. But the infrastructure side has gone from that core now, or big server rooms and stuff, to being distributed itself. Right? The network topology is almost, it's weird. It's like changed from being this central thing where everything talks to the center, now to just being spread out all over the place. And we get the so-called cloud. Yeah, so it's exciting times to be alive. It really is, with this, the cloud stuff taking off. So, I said this before, a lot of embedded system subjects that are out there are what are called hacking subjects. You're going to learn a bit about a particular microcontroller, you're going to plug it into something, if it doesn't work, you turn it around the other way and it seems to work. You might memorise a few basic rules of thumb about do this, don't do that, but have no real understanding of why that's the case. You just learned it because someone told you to learn it. All right? That's hacking. That's just putting random things together and, yeah, sure, they work. Things can go wrong. Indeed, they do go wrong. It's okay for simple stuff, but for the bigger projects that are now evolving, in particular, life-endangering projects, autonomous cars, hello, this stuff has to be properly designed from a theoretical perspective. You need to be able to prove that this thing is not going to crash and burn, right? Not just say, oh, I tried it out once and it seemed to work, right? And it's okay, but you need to prove that it can. I'm going to show you an example in a minute where a reachability analysis is done on a particular design. We'll actually be covering that in the lectures later on. So the focus is on model-based system design and on embedded software. It's not going to be about reading a data sheet for a particular microcontroller and soldering it to something else and frying it and then trying again. Okay? It's about the lectures and the theoretical part is going to be about model-based system design, and the embedded software is what you're going to be doing in the workshops, which will support that as well. Okay, so obviously we're going to be doing this in these sort of 3 phases, and we're going to chop and change between them. That's all right. We're going to model. I'm sure you pretty much understand how to model things, right? It's about expressing what a system does. That means, obviously, well, we may have to go to physics. For instance, physics is very common with cyber-physical systems. maybe less so chemical stuff, more often physics, or should do. Design. I'm pretty sure we have a good concept of what design is about, how a system does what it does. And lastly, the analysis part. And this is where I think in terms of how we're going to follow the book is going to fry your mind a little bit about being a bit more rigorous about specifying why a system does what it does and knowing when it fails, why it fails. That's the problem with the hacking approach. And I've seen it where I have had capstone students put together a few bits and pieces to make something and it's failed and they've got no way of knowing which component caused the whole thing to fail. They've just got no way of doing it because they didn't do a proper analysis of the system. Okay, so I'm going to give you a nice little example. Quadcopter, quad rotor, drone, whatever you want to call it. Technically, it's a quad rotor. This is a one developed out, I think this is a Stanford one here. It's a very basic quadcopter. And this is not just a commercial one you go and buy. This is one that was built over in the US. And what I want to point out is the process that was followed follows exactly the course of the text, if you think about it. This is not, once again, about going buying some props and a motor and hooking up a microcontroller and just getting it up there. You need to know the dynamics of the damn thing first. You've probably got to sit there for a few weeks or months and work out the physics of it. Not next week, in a few weeks' time, we're going to model a helicopter model. And you already see that's a difficult thing to model. You've got 3 dimensions, but you've then also got rotations in those 3 dimensions as well. Very difficult thing to control. Right, so flight dynamics. Modes of operation. If we think how a program is going to work on this, it has to work in different modes. There's a mode for takeoff. There's perhaps a mode for just cruising along. And there's also a different mode for landing. And the dynamics could be very different with those different modes. Okay, so the model may be changing depending on the mode that we're in. This is new stuff to think about. This is not get a physics model and just hack a solution to it and you're done. This is where you may need multiple models and you're switching between modes. How do you make the switches continuous? What if you can't just make changes in motor speeds and stuff be discontinuous, right? The thing will just fall out of the sky. So how do you switch between modes? Very important thing we're going to talk about. Subsystems as well, so composition of behaviours and then possible multi-vehicle interaction. We're just adding extra layers onto it. That's before we've even done the design. Then you do design, right? Sensors, actuators. You have to learn how they sample the real world and understand that there are inherent problems with that. Sensor error, sensor drift, all that sort of stuff that we have to combat. These things could be critical and basically kill someone if you don't take it into account. That's the cyber-physical part. The sensor part is the input part and the actuators are the output parts, if you like. Okay. Concurrent software. We're going to talk a bit about this next week, about parallelism and stuff like that. But so real-time scheduling. What's real-time actually mean? Well, for a drone, you have to react pretty quickly to disturbances. Okay, if you get a sudden, impulse, so someone decides to throw something at it, or maybe you get a very strong gust of wind, you need to react almost in real time, but there's no such thing as real time because there's always processing delays in things as well. What does real time actually mean? And if there's a processor sitting on there churning away, how long does it take to do that? And more importantly, how long does it take to get the feedback back from the actuators in response to a command that the brain has issued? Very, very difficult thing. You're going to find it very difficult. And then lastly, you can't debug this thing while you're flying it. You need to provide, particularly if, being an engineer, if you go out into industry, you need to certify this thing with your neck on the line to say this is safe to fly. Okay? And not just, oh, I just did a quick test over there and it didn't tip or anything. You need to do it without testing it, without flying it as such. So how do you actually verify safe behaviour? And lastly, this is one that has popped up recently, how do you make sure that someone doesn't hack into the thing and just fly off with it? Right? That's something else we have to think about. Now, that is a block diagram of what's in that particular drone. And this example is used because it's obviously developed at a uni, so we know exactly what's inside. It's not a closed proprietary design like a DJI drone or something like that. And you'll see the complexities here. On the left, in green and underneath, there are all the actuators, sensors. Well, and actuators as well. The motors are the actuator parts. But these are all the sensors. You've got LiDAR. You've got a stereo camera system on there, right, to detect objects. It's object detection. GPS for positioning. An IMU unit for more precise positioning. You've got altitude ranges as well. And then a beacon tracker thing as well to track where it is. A lot of those things, there's 3 microcontrollers in here, all with different architectures. Wow. It's a cyber physical system. This guy here has no operating system on it. It's an ATmega 128. It is just runs some very basic machine code on the thing. Why don't we have an operating system? We can't afford the problems that an operating system give us at the low level. This thing here has to react damn quickly to disturbances, tell the motors what to do, and be calculating its orientation and stuff from the inertial measurement unit here. Okay? It can't just sit there waiting for some other process to happen, right, on an operating system that may have multiple things being allowed to happen. Up here we've got sort of more complex processes here that will have an underlying operating system on there because we're going to do more, with this you do more high-level tasks. So for instance, broadcasting back data or control signals, or for collaborative stuff you might want to broadcast to other units running nearby to do cooperative stuff as well. So this is a difficult problem. In here, we have the fusion of sensors operating at different rates with different tolerances and all sorts of things on there. And combining them all together in order to drive this thing is a very difficult problem, very difficult. It might be easy in physics if you just had the differential equations and the integrals and stuff and you could write out a beautiful equation for it. That's great, that's the modelling part. That's easy, that's really easy, that's well understood. This stuff is difficult and changes. If you go and swap the GPS unit out for another GPS of a different brand, maybe with a different sampling frequency or something like that, it could radically change the behaviour of the system. Okay, those C calls in the code that's running on here now may have to change according to the data that's coming back from here. Oh, you've got to change your code? Yep, you do. All right, I'll show you a quick video of this unit. But I'll show you, because we're getting close to finishing, I'll show you computer music. Right, so how do you prove that this thing can do a backflip? How do you prove it? Well, you need to do what's called a reachability analysis on it. So I'll put the bit of music on. So can it do a backflip without actually just going and testing it to see if it does? So there are 3 modes of operation, right? Give it an impulse to get it up there. A drift stage. Oh, what? Thank you. It's on the other monitor. I hate dual monitors. Which side is it on? That one. Thank you. Now I can't control it. Ah. Oh. Okay, so let's get back. Right, there are 3 modes of operation. It's not trivial changing the operating conditions, right, as it's in a different mode. You've got a switched system that has to suddenly change the model of the system based on what mode it's in. The dynamics could be different as well. So here we go. How do you prove that it can do a backflip? Right, that's its goal. Just flip it. There are 3 modes. Give it an impulse to get it up into the sky, basically high enough. You've got to generate torque to get it to rotate. Then you have to turn the motors off while upside down, otherwise you're going to fly into the ground. And then you've got to turn them back on to stabilise it in order to get it back to level flight. So bad things can happen, right, if you don't get the timing right. Too early or too late, you could be in trouble. So when do you determine the safe switching conditions in order to get it to do that? You need to do a reachability analysis. So if you're plotting the angular velocity versus the angle, you can basically show these regions where certain things are safe. And the transition to those regions are going to be the goals of each of the other stages. Okay, so you've got goals of those stages to be in the region of the next mode of the system. The theory is sound. Now, as for practice, right, let's see. Can it do a flip? It's even got a countdown. Nice. Yeah, did it. Okay. And that was starting at fairly low. This is starting very low, so it's probably on the edge of its operating parameters. Yep. And just recovered in time. And then decides to fly away or something. Is that the end? Yeah, that's the end. All right, so that's from Berkeley, actually. All right, now, how do I get my screen back? Screen, where are you? Mouse, where are you? Yeah, all right, I don't want to see you. It is a stand for test bed, I thought so. Okay. Okay, so any subject or course that tells you how to design embedded systems is not telling you the truth. Because technology will change. And when technology changes, things change as well, right? So the goal of this subject is not to teach you about the technology right here, right now. We need to use that in the workshops because you've got to see stuff happen. But the lectures is not about the technology right here, right now, and locking in on one particular thing. As you'll see next week when we look at processors, we're going to talk about every sort of processor out there. Okay? So you guys are going to be the engineers of the future. You're going to take this knowledge and be able to apply it to whatever is around in 5, 10, 15 years' time, because who the hell knows? All right. We're going to leave it there for this week. Next lecture, we're going to do sensors and actuators. You'll never look at another sensor again after you see that lecture. And then we'll do embedded processors as well. So see you all next week. Hopefully my voice will be a bit better.